Operations with radicals is really important, but it's not long, it's not short, and I wouldn't, if I'm going to devote time to it, I'm not going to worry too much about it. But I do want you to realize that if I take a square root of 5, let's say, sorry about my writing, and multiply it by the square root of 5, that's the same as saying square root of 5 squared. And when you have a square root and a square, they essentially cancel out. And the answer will always just be the number inside the square root. The same is true, and just as an aside, you're not going to have this many times. If I have the cube root of 5, which is designated like this, it becomes the cube root of 5 to the power of 3. And those also cancel out, and the answer is 5. You can also realize this when you take 5, and let's just make it big here, and you realize that the cube root is the same, or the square root is the same as 5 to the power of half. And when I multiply a 5 to the power of half times a 5 to the power of half, the rule is when the base is the same, you add their exponents. What is a half plus a half? It's 1. So you get 5 to the power of 1, which is simply 5. So you can see that if you break it into exponents as well, it works out. Same with the cube root. You'll also discover this nifty thing. Often you might be wanting to get rid of a square root at the bottom of the denominator. And the reason for this usually is when you're trying to add different fractions. Let's say I have 2 over these 2 square roots. When I'm looking to add it to, let's say, a third, it's a big pain to figure out what to convert the denominators to add them. It will take me quite a bit of time. Some of you are fast at it, but there's many reasons to get rid of a square root, especially when it's something like square root of x, because you don't want the square root of a negative number down there. But what you're going to discover is if you multiply it by the conjugate, so what is the conjugate? What's a conjugate? It's the same thing, but instead of the plus sign, it's the opposite sign. So you're not allowed to multiply a fraction by just something on the bottom. You have to multiply top and bottom by the same thing. And then you're not changing it at all. But focus on the denominator. And it's a distributive rule like anything else. So what's square root of 5 times square root of 5? We've already learned that that's 5. Then what's square root of 5 times negative square root of 3? It's negative square root of 5 times the negative square root of 3. But then what's plus square root of 3 times plus square root of 5? It's the same thing. It's plus. It doesn't matter what order these are in, by the way, when you're multiplying them. And we can see right away this middle term will always cancel out. It's like a difference of 2 squares. The middle term will always cancel out. And then the last one, plus square root of 3 times minus square root of 3, will always be minus the 3. We suddenly can get rid of that entire middle term, and we get 5 minus 3 when we multiply the denominator. What's 5 minus 3? It's 2. It won't always work out to that nice 2. It depends what numbers are in there, but we can see that the denominator becomes 2. And then what does the top become? It just becomes 2 times this and 2 times that. And you get a 2 square root of 5 minus 2 square root of 3 all over 2. Now I also want to suggest to you that we don't actually have, we can simplify it even more here. It just so happens the 2 at the bottom, the 2 at the top is multiplying this bracket, and then it's being divided by 2, and we can see that they just simplify like that. And this is what we end up with. It just ends up being this. And if you want to check that out, you can always take 2, divide it by this. Remember that we had it like plus before. It's not always going to become smooth like this. And we can't do anything more than that because you can't subtract square roots that are different numbers. But let's just take this and see what it comes to, and then we'll take this and see what it comes to. So when I do 2 divided, and I have to do a brackets here, square root of 5 plus square root of 3, close brackets, equals, I get 0.504. So just remember that, 0.504. And now on the left, we're going to do square root of 5 minus square root of 3. And we get the same number. So you can see that this is much easier to work with than this. If I had to add a fraction or anything else, it's much easier. Now the denominator is not always going to cancel out like that. Let's say if this had been a 3 up here, it would be 3 and 3 here. And it would all be over 2. So they're not always going to cancel out. But it's much easier to work with. And you can still express them like this, where it's 3 over 2 times square root of 5 minus square root of 3, if you have a reason to keep the numerical separate from that. Much easier to manipulate, and it's something that this chapter is teaching us. So we're going to get right into it. And they walk you through it, and they explain. And the other thing you want to get used to is simplification of a square root. And when you look at it, when you look at square root of 18, there's not much we can do to it until we realize that that's the same as square root of 9 times 2, or 18 is 9 times 2 in there. Well, you're allowed to break that up. And you can always test yourself and figure out if this is true. And obviously the square root of 9 has a square root, and you're left with 3 square root of 2. And this is the simplified mixed, it's called mixed radical because it has a whole number and a radical of this. And this too you'll find will be useful. Now the last rule is we're not able to add things. And let's see, what would be a good one? Yeah, we'll do 8. We're not allowed to add these two things, except that 8 here can be rewritten as 4 times 2, which can be rewritten as 4 times square root of 4 times the square root of 2. And of course the square root of 4 has a solution, so we get 2. And now essentially I have 1 apple plus 2 apples, and I get 3 square root of 2. So suddenly I could add them by simplifying one of them. So that's another rule. And I think that's about it for that. So that's what this chapter deals with. So you can see mixed radicals. So they want it to be converted. And the secret to them is always remember your big square roots. What are your big 10 square roots? So let's go through. To do that, you can just look at what the squares are. So if I go 1, 2, 3, 4, 5, what are the big square roots here? Well, square root of 1. What is the square of 2? 4. So here we go, 9. And the square of 4 is 16. And 25. And I do the other ones, but you can just do this now. So that means I should always be looking for these big numbers in here, somewhere in there, to see if these numbers are divided by 1, 4, 9, 16, 25. Of course, the other ones are 36 for 6, 49 for 7, 64 for 8, 81 for 9, 100 for 10, so always look out for 100, 121 for 11, and 144 for 12. So that's the other thing to look out for. Can these numbers be divided by any of those numbers that I just went through? So let's look at 27. Well, the first thing you should ask yourself is, can 27 be divided by any number? So we're looking at these here. Can 27 be divided by any number? Yeah, it's clear it can be divided by 9 and 3. 9 times 3. So I can put that under the square root. And then eventually, after I'm done putting it under the square root, I can break it up as individuals if I want, but you don't have to. And it's clear the square root of 9 is 3, and the square root of 3 must be left alone. So that is the simplest mixed radical of that. And you often want to express it like this to make certain graphs more clear about what's going on. Because when you look at square root of 27, you don't have a clear idea of what it is. When you look at 3 times the square root of 3, you know it's around 4 something. Gives you a better idea, an instant image of what number you're dealing with, which can matter when you're trying to figure something out. What about b? Well, immediately I can say, well, if for b, I could make the mistake of going 5 times 10, but neither one of these has a square root. So you immediately want to say, oh, wait a minute, it's 25. 25 times 2 is the square root that I can fit into there. And of course, the square root of 25 is 5 times the square root of 2. That's how you do these over and over again. Ask yourself, what number can divide into 50 that happens to have a natural square root? And those numbers I went over for natural square roots are the ones to look for. Okay, what about C? C looks like it's 2 times 49. And so if I do 2 times 49 inside that bracket, 49 obviously has a square root of 7. So I get 7 times square root of 2. Also note, it's a good idea to always have your whole number in front as the multiplier, as opposed to this. Simply because you can lose track of, if you have to add or multiply other numbers, you can lose track of what you're multiplying. Always just follow the same order. It's also why we always say 7x instead of x7. It's so that we have a consistent place to look for our numbers. And what's 32? It's 2 times 16. All under square root. And of course, the square root of 16 is 4. So we get 4 times the square root of 2. And you can see how easy those are. Now, the good news for multiplying square roots is you simply multiply the numbers first, and then you multiply the square roots. So in this case, you can just multiply inside here in 35. And sometimes you'll want to look for other simplifications, like maybe you can divide this by 9 or something. But in this case, we've only got 5 and 7 are the only factors. So there's nothing more to simplify, and that's pretty much the answer of that. This is the same thing. I can see it's 6 times 11. And it's the square root of 66. And again, if I look at 6 is the only one, I could divide it by 3 and it's 22. But neither one of those has a square root that's natural. So that's probably the only one. Now for this one, you multiply the whole numbers first. So what's 2 times 5? It's 10. And what's 3 times 2? It's 6. And if somebody wanted you to express that just as a square root, well, what number makes a square root of 10? 100. Square root of 100 makes 10. Sorry, what number square rooted becomes 10? Which means I can express 10 like this. It's the same thing. And then when I multiply it, I get square root of 600. So that's the whole radical form. And this is the mixed radical form. There's no real reason to go to this unless you have to or need to. Because you can still just pull the same numbers out. And then what about this one? We got a negative, so you just follow the same rules of multiplication. What's negative 4 times positive 8? It's negative 32. And then what's square root of 3 times 13? It's square root of 39. And always look and see if there's some way to pull out a natural. So the natural's at this level. 49 is too high, so we're looking at 36, 25, 16, 9, and 4, none of which go into that. So this is the simplest form. Negative 32 times the square root of 39. And then they get you to do it over and over again, but they want you to see if you can find ways to, in this case it's adding, and actually surprisingly, adding is a little bit more difficult than multiplying, which is true for fractions too. Adding fractions is more difficult than multiplying fractions. Well, we can only add things that have the same root. I've got 4 apples plus 3 apples, so I got 7 apples. That is that. I've got 9 apples minus 4 apples, so 9 minus 4 is 5 apples. It's the same way if you would take 5x minus 3x. You've got 5 apples minus 3 apples, you've got 2 apples. That's really how you got to think of anything that's unknown or unsolvable. These you have to regroup in what you can add and what you can't add. So it's clear that if I rearrange this, I want to rearrange based on apples and oranges. So here I have 3 apples minus 4 apples, so I got minus 1, or just minus apple. And I got 8 oranges plus 11 oranges, so I've got 19. Sorry for my handwriting, 19 oranges. And it can't really get simpler than that. You can look for ways to turn this into square root of 2 and this into square root of 3 if they were bigger numbers, but they're not. So this simplified form is negative square root of 3 plus 19 times square root of 2. And then this one, they're obviously wouldn't give this to you unless there was a trick. And you can't really do much with this. So you got square root of 2 times 4 times the square root of 4. What's the square root of 4? It's 2. So 8 simplifies into 2 square root of 2. And then if I look at 18, I can do 9 times 2. And the 9 can come out, so I got minus 3 square root of 2. So suddenly I have 2 apples minus 3 apples, which is minus 1 apple. So here you had to break it down into some, to see if there was some radical in common, because you can only add or subtract radicals that have the same number. So I'm going to take a little break here and continue in a second. These are pretty much the same idea, but you'll notice they're already mixed radicals. What do they mean? Well, they say in simplest form, which means all of these will have a better way to get smaller. So let's start with just looking at them first. How can I make square root of 12 even simpler? Well, it's 3 times 4 in there, or putting it this way, 3 times 4 all over square root. And it's clear that the square root of 4 is 2. So this is the simpler way of expressing square root of 12. Once I have that, I can multiply it by the number that's in front. So I got 3. 3 times 2 is 6. So that means this whole thing simplifies to 6 times square root of 3, right over here. But obviously the key is always finding how to express these simpler. So looking at 125, it's clear to me that that's going to be 5 times 25. And you can even go faster. You can just say, okay, well, 5 times 25 in here. That means the square root of 25 is 5. So really, square root of 125 is 5 times square root of 5. And then when I multiply this minus 5 times the 5, I get minus 25. So it's minus 25 times the square root of 5. And that's the simplest mixed fraction of that. What does square root 40 simplify down to? Well, it's 4 times 10. So I can just say 4 times, and here's where I get faster, so I know I can't simplify the 10. So it's just going to be, what's the square root of 4? It's going to be 2. And then when I take this 2 and multiply by 10, I get 20. So this is the simplest square root mixed fraction of that. And they're all like that. So we're focusing on the 60 here. Well, 6 times 10 isn't going to do it. 3 times 20 isn't going to do it. There is definitely a 4 times 15 factor going on here. And when I square root that, the 4 becomes a 2. So I'm dealing with 2 square root of 15. And 15 can't really be square rooted anymore, or it can't be simplified anymore. 5 times 3 Doesn't simplify, but the 2 times the negative half, the 2's cancel out, and I'm just left with negative 1. So that just means that in front of this would be a big old negative symbol, like that. And what about this square root of 45? It's clear it's, oh, that's a good one. Let's see, 25, no. 4 times something, 4 times, nope. So what's the next one? 9 times 5, obviously. So I had a little brain fart there. Square root of 9 and 5, so I get 3 square root of 5. And when I take this 3 and multiply it by 2/3, the 3's cancel out. And I'm left with just the 2. So this whole thing simplifies to 2 square root of 5. And you can always just take the square root of 45, multiply it by 2, divide it by 3. Then you can take the square root of 5 and multiply it by 2 and see if you get the same thing. And you should. Okay, and what about this other one? So 12, you can immediately see, you might be tempted to go, oh, it's 12 times 100. And 100 has a square root of 10. But 12 can also be broken down into 3 times 4. And so we can just focus on this part of it. 3 times 400, and the square root of 400 is 20. So that means this 1200 simplifies into 20 times the square root of 3. And then the 20 has to get multiplied. Where was it? 1200. Where was I on this? Oh, this one here. So now I have to multiply that whole thing by minus 9 over 10. Okay. The 10's cancel out into this. What's 2 times minus 9? Minus 18. So that whole thing simplifies to minus 18 times the square root of 3. And they're all like that. Okay, so this one you have to distribute and then see if there's any way to simplify it. And actually, I would argue that this is the actual simplified form already. But I don't think they want that. So this to this and this to this simply becomes 2 square root of 3 minus square root of 3 times 5, it's square root of 15. And as we already learned earlier, square root of 15 cannot be simplified. So this is what this distributes into. I would argue that this is not the simplified form. I'd argue that this is, but that's okay. Okay, so in this you just want to focus on the numbers can multiply the numbers, and the roots can multiply the roots. So in this first one, I'm left with 2 times the square root of 14. And then 2 times 3 is 6, and square root of 2 times square root of 3 is 6. So I'm left with 2 square root of 14 plus 6 square root of 6. Now you should always look and see if these can be simplified further, but in most of these cases they can't, and that's the simplified version. In this case, it's interesting. When you have a bracket, try to remember the rule of exponents says that the 4 also will be squared, and the square root of 2 will be squared. And it's quite clear that the square root of 2 squared is just 2, and that the square of 4 is 16, and that 16 times 2 is 32. Right? And then D, it's the same thing. The rule for powers is that the power applies to both things in the bracket that are multiplying each other. So I get negative 2 to the square power of 3. And I also get square root of 3 to the power of 3. Now that's interesting because that's the same as, well, if I want, the easiest thing is to put that as square root of 3 is to the power of half. Well, no, I'm going to leave it like this. Square root of 3 times to the power of 3 is the same as square root of 3 times the square root of 3 times the square root of 3. These first two just become 3. So square root of 3 times square root of 3 is simply 3. So that means square root of 3 cubed is 3 times square root of 3. This one here, minus 2 to the power of 3, don't get confused. Minus numbers to odd powers stay negative. So I get negative 8 times 3, which is negative 24, times the square root of 3. And that's my answer for that, right there. That's the simplified version of that. And then this, you can only multiply the numbers times numbers, but this is an example of one where the roots will be able to simplify easier. 4 times 3 is 12. And 3 times 6 is 18 inside the square root of 18. However, that can be simplified to 2 times 9. Which means the square root of 9 can come out, and I get 3 times 12, which is 36. And I'm left with a square root of 2 in the brackets, in the radical. 36 times square root of 2 is the simplified version of this. And then finally this one. So when I multiply the negative 7 times 5, I get negative 35. And when I get 2 times 8, I get 16, square root of 16. However, the square root of 16 can be solved. It's 4. So I get 4 times negative 35, which is 140, is the answer. That's the only one that has a nice, clean answer. And moving on, you'll discover this whole chapter is just about figuring out simplified forms. 6 times 7, or 6 and 7 rather, is all the same thing, except now we're facing situations where we have to subtract. Well, you can only subtract when when the base is the same. So clearly the trick here is going to be figuring out how can I make the lowest base of 8? Well, 8 is 2 times 4. The square root of 4 is 2, so I get 2 square root of 2 for this one. That's what square root of 8 becomes. And if I look carefully at 32, that's the same as 2 times 16. Which means the square root of 16 is 4. So I got minus 4 times the square root of 2. And now suddenly their base is the same. So I have 2 apples minus 4 apples. And I have minus 2 apples. Or in this case, minus 2 times the square root of 4. You can only add and subtract things when their base is the same. So obviously all these questions are going to be like that. Notice on some of these mixed questions, you're going to have some that can add and some that can't. Square root of 12, you should already know, comes down to 2 square root of 3, using the methods above. 18 becomes 9 times 2, which is 3 square root of 2. 27 is 3 times 9, which comes down to, since it's a minus 3. So 9 times 3, square root of 9 is 3. 9 times 3, yeah, which is that, becomes negative 3 square root of 3. And finally 50 is not 5 times 10, but 2 times 25, and 25's square root is 5. And you've got to leave the 2 inside the bracket. Let's see if I can just, there we go, like that. And then you got to look for your apples and oranges. Well, 3 square root of 2 plus 5 square root of 2 plus 2 square root of 3, and don't keep in mind that there's an invisible plus in front of it, minus 3 square root of 3. So here I got 3 apples plus 5 apples, that's 8 apples. And here I've got 2 oranges minus 3 oranges, so that's minus 1 orange. So it ends up being this. 8 times the square root of 2 minus 1 times the square root of 3. Just like that. That's the simplest form of that mess. So they're all like that. So just focus on sometimes the square roots, because the only way you can add them is if they have a shared base. So let's see, 49 times 2 here. Square root of 49 is 7. 7 times 3 is 21. So this simplifies to 21 square root of 2. This is 36 times 2. Square root of 36 is 6. 6 times minus 5 is minus 30 with the square root of 2. And suddenly we have 21 apples minus 30 apples, which is clearly minus 9 apples. And that's all they are. You've got to obviously figure out how these can be broken down into some of the basic square roots, which is, again, these are the basic square roots you should always be looking for. 144, 121, both square root of 12, square root of 11, 100, square root is 10, 81, square root of 9, 64, square root is 8, and then 49, square root is 7, 36, square root is 6, 25, square root is 5, 16, square root is 4, 9, square root is 3, and 4, square root of 2, and of course 1, square root of 1. But that's almost useless, the square root of 1. And they're all going to be about that. Can you find out how they break down? So obviously square root of 200 is 2 times 100. That means I can take the square root of 100 and times it to minus 4. The square root of 100 is 10. So I get minus 40 times the square root of 2. And then 242 looks like it's 121 times 2. So I get 5 plus 5 times 121 in the times 2. The 121 is 11, so 5 times 11 square root of 2, which is 55 square root of 2. Suddenly I have apples, and I've got minus 40 apples plus 55 apples, and that's 15 apples. Whenever you're adding a negative number to an addition, you can also flip them around to make it easier to see what's 55 square root of 2 minus 40 square root of 2. It's obviously 15 squared times square root of 2. But it's the same rules. You can only add them with the same base, and the base doesn't disappear. It's like adding apples and oranges. And these are all the same. 45 breaks down into 9 and 3. No, sorry, 9 and 5. So you get minus 5 times 3, which is minus 15, square root of 5. 52 breaks down into not 36, but into not 25. Geez. Let's just divide it by half. 26. No. 13 and 2. 4. It divides into 4 times, let's see, 26, 13. 4 times 13, like this. Square root of 4 is 2. So I get plus 2. Square root of 13, kind of a weird one. And then 25, it's 5 times 25, which is square root of 5 is 5, so I get 15 square root of 5, like that. And you can see the only apples I have in common here are these apples. They cancel out, because I have 15 apples minus 15 apples, and I'm left with 2 square root of 13 as the final answer. Now, if you were to use a calculator and do all these multiplications, square roots, and then add all of them together, this is what you should get. And then these, they just make it tough with the fractions. But the square root of 12 breaks down into 2 times square root of 3, and 2 times 7 is 14, so you get that for the first one. (28) breaks down into 4 times 7, and that's minus 3 times 2. Once square root of 4 comes out, you get minus 2, 6, square root of 7. 48 breaks down, we just did it. It was, oh, geez, times 12. It wasn't 4 times 12. It was 16 times 3. So this breaks down into 16 times 3. Square root of 16 is 4. 4 times a half becomes 2. So you get plus 2. And square root of 3. We've got a couple apples there. And finally, 63 is tricky, but it looks like 3 goes into it 21 times. So that means there's a 7 times 3 as well. So you got 9 times, obviously you got 9 times 7. So you get 9, 2/3 times 9, square root of 9 times 7. And so the 9 comes out, becomes a 3, and the 3's cancel out. So you end up with plus 2, square root of 7. Notice that a lot of the hints will be, if you get a square root of 7 over here, you're probably going to get a square root of 7 over here. So I got 14 apples plus 2 apples, so I got 16 apples. And then I've got minus 6 oranges plus 2 oranges, so minus 4 oranges. And then I've just got to make sure I put my radical signs over the right thing. And that's the simplified version of this. This is expansion. I don't know if I should even bother with this. Just keep in mind that square roots times square roots will just be the square root of the number, so square root of 50. Also keep in mind that sometimes you can just simplify things. This just means the whole bracket times itself. This is a conjugate. So 2 times the square root of 2 is 2. Square root of 2 times minus square root of 5 is minus square root of 10. But then I get plus square root of 10, so they nullify. And then I get minus 5. So I get 2 minus 5, which is equal to minus 3. So that's a very important concept, conjugate. So simplifies just a very simple number. So get rid of that. Is this a conjugate? No, it's close. So we'd have to add it up. That's not a conjugate either. So a lot of them is, what's 6 times 3? It's 18. What's 6 times 2 times square root of 10? It's 12 square root of 10. What's minus 5 times 3? It's minus 3 square root of 5. And then finally, what's negative 5 times square root of 10? It's negative square root of 50. And sometimes you'll be able to find ways to simplify things, like this is 25 times 2. And sometimes you won't, like square root of 10 does not get simplified. But you should always look at ways to simplify it further. So just to do that one again, it's 18 plus 12 square root of 10 minus 3 square root of 5, and then finally minus 2 square root of 50, but that comes minus 2 times 5 is 10 times 2, something like that. So this is what you get. And then you should always look for ways to possibly simplify this so that these can add or these can add. But there's really no way to simplify the square root of 10 or square root of 5. You could come up with a weird square root in there for sure, but it won't serve you much purpose. Like for instance, I could take 10 and divide it by 4, and I would get 4 times 10 over 4 essentially. And then I could take the square root of 4 and come up with 2, and I'd end up with 2 square root of 10 over 4. But that's kind of useless. Doesn't serve me any purpose and actually makes it more complicated. Okay, so this is simply itself times itself. So you're going to get 2 times 2, 4. 2 times 3 square root of 3 is plus 6 square root of 3. Plus 3 times 2 square, plus 3 square root of 3 times 2 is 6 square root of 3. And then plus 3 there is plus 9 times 3 plus 27. Then the middle terms add up. And I get 4 plus 12 square root of 3 plus, let's see, 9 times 3, 27. Now I want you to notice that this follows the same binomial expansion as all of them. It's the square of term A plus the square of term b plus 2ab. So you can do this one like that as well. So it's still binomial expansion when something's squared. To rehash that, a binomial expansion, it means anything squared, any two terms squared, is going to be equal to a squared plus 2ab plus b squared. So ab squared will always equal this. And you should learn that because it'll make expanding these things easier. So here, 3 times this, I get 3 times 3, I get 9. And then this, I get minus 6 square root of 6. And this, I get plus 4 square root of 6. And this last one, I get minus 8 square root of 4, which is 2. So it's minus 16. I could say 9 minus 16 is minus 7. And minus 6 plus 4 square root of 6 is minus 2 square root of 6. So this is the simplified version of that. And it's just expanding and following the same rules. Using the binomial theory of this, the first term squared is going to be 4 times 5, 20. The two terms multiplied, so I get 2 times 3 is minus 12. And then I don't have to multiply the internal ones times 2 because it's all only have to multiply one of them. So I get square root of 35. And you should always check to see if that can be simplified, which it can't. And then the last term is minus 3 squared is plus 9 and times 7, which is 63. And then 20 plus 63 becomes 83 minus 12 times the square root of 35. And that's the simplified answer of that. And I used binomial expansion to do it. Please note that when it's a minus here, the only thing that changes is it's a minus here. Everything else stays plus. That's because a square plus that. That's because any negative that's squared becomes positive. And then finally the last one is a trinomial, so you got to do it twice, so it's kind of a pain. And I'm not going to bother with it. That's straightforward, just expansion. And then let's see, calculate the length of a diagonal square with a side length of this. Okay, we'll try a couple of these. These are all best served when you draw them. So calculate the length of the diagonal of a square. So keep in mind your knowledge of squares means all sides of this square are going to be 4 centimeters. If you look at a diagonal, it also means they'll all have 90-degree angles. And that means if you look at the diagonal, we can ignore half of this square. We can see a Pythagoras Theorem going on, which means this h is going to be this squared plus this squared. Well, 16 squared is 32, so it's square root of 32. But they probably want it in simplest form. Exact values, express your answers in simplest form. Square root of 32 is 16 times 2, which means 4 square root of 2 is the length of this hypotenuse. So that's just the Pythagoras Theorem. A square has an area. Calculate the side length. Okay. So if we have a square, and we can know that just each side is going to be side x, but that all sides are x, we know that the formula for the area of square is x times x, or x squared. And we know that x squared in this case is going to be equal to 450. We don't have to worry about the negative results because areas will only be positive. But if I want to solve this, I got to square root both sides. And then quickly you should say to yourself, okay, obviously in this section, this can be simplified somehow. And I see a 25 in there, but there's probably more. So I can see that it's 25 times 4 times 8 times 10. Oops, it's not times 10. It's 25 times, let's see, 4, 8, 16, 2 more, 18. But I can also see 18 as 9 times 2. The square root of the 9 is 3. The square root of 25 is 5. 3 times 25 is 15. So clearly I have this is the answer. The length of any one of these sides is 15 square root of 2 is the length of one side. And you can prove this to yourself by multiplying it 15 square root of 2 times itself. So 15 times square root of 2 is equal to this. That would be the x. And then when you multiply x times x, you get 450. Okay, and the last question is, in 10 anyway, determine the length of the diagonal of a rectangle. So now you've got to use your knowledge of the rectangle. But they give us the length and the width. And fortunately, a diagonal is still going to have a right angle right here. So that means this diagonal is simply the hypotenuse. And the hypotenuse is simply going to be the square root of 9 squared, or 81, plus 3 squared, or 9, or the square root of 90. So in other words, h squared is equal to 90, but h is equal to the square root of 90. And quickly I can say, well, that's 9 times 10, so I got 3 times the square root of 10. And that's going to be this diagonal right here. Let's see if I can finish the others quickly. This is just all about remembering how to do a length of a line segment. And actually, they want me to do it in Pythagoras way, but I could use my knowledge from grade 10 for line segment, which says this. So I'll pull up 11 and 12. The rule for a line segment of between any two Cartesian points is the square root of y2 minus y1, which is the rise. So I'm going to call this y2 minus y1. So I get 6 squared plus x2 minus x1 squared. That's the formula for any line segment from grade 10. And the x2 is minus 2 minus 4, so I get minus 6 squared. So notice that I get 36 plus 36. Another way of designating that is 36 times 2. 36 has a square root. It's 6 times the square root of 2. So that is the line length in simplified exact terms in the simplest form between these two Cartesian points. You could also, if you had forgotten how to do line length, you could map this out as point A going to point B, and you'll realize that this length here is x2 minus x1, or 4 minus minus 2, 6. And you'll realize that this height here is y2 minus y1, or 7 minus 6, and you can do it that way as well, using Pythagoras' theorem. Calculate the perimeter and the area. Well, area is base times height times half. So if I multiply this by half first, I can just get rid of these. And I'm left with 3 times the square root of 2. 3 square root of 8 times square root of 2, which is 3 times the square root of 16. Well, the square root of 16 is 4, so that means the area of this triangle is 12. You can confirm it with a calculator. You can just do 3 times 2, 6, times the square root of 16, which is just going to tell you is that, times a half. And then the perimeter, you have to add them all up together. 2 plus square root of 2 is as simple as gets, but 3 square root of 8 can become 6 square root of 2. And obviously we're going to look for ways of becoming square root of 2 with the 80. So I know that I can do 4 times 20. And I can do 16 times 5. So square root of 16 is 4. So I get 4 square root of 2. So I get this for the perimeter. And I can't add these apples. These are oranges, but I can add these apples. And this is the simplified perimeter in exact numbers of this. And why do we like exact numbers? Because if I turn these into decimals, it goes on and on and on, and I have to round it up. And as soon as I round up a number, it's no longer accurate, whereas square roots are incredibly accurate. And then this one, you could just sub in a number like 1 or 2 would be better. Or 4. Let's use 4. What's the square root of 4? And square root of 4, we can make them the same. So square root of 4 is 2 plus 2 squared is 4. Squared is 16. Over here, we get 4 squared and square rooted. So essentially, it just becomes 4 plus 4, which is 8. So this one will always be bigger. Now you can, obviously they want you to prove it algebraically. But that'll give you a hint if you're not sure, so that you can put yourself on the right track. Okay, notice that this second one is easily solved because the square root of a square is simply canceling out. So really it's a plus b. And notice that this one is simply itself times itself. And I can just use my binomial theory. And it's clear that the first one is going to become a, and the last one's going to become b, and then I got plus 2 times square root of ab, like this. Well, right away, like this. That's the binomial expansion of this, just itself. But right away I can see a plus b here and a plus b plus another amount here. This is always going to be more than that. Because this has everything this has plus 2 times square root of ab. And as long as a and b are above 0, as in this question, this second part will always be more than that one. And then give 3 mixed radical equivalents to 200, which answers the simplest radical form. Explain how you know. Really? Kind of a waste of time. Okay. Well, you can go 100 times 2. So that's 10 square root of 2. So far, that's the simplest form because that's the smallest radical I can come up with. So 10 square root of 2, I would say, is the simplest one. But you can also do 4 times 50. So you get 2 square root of 50, which obviously is not the simplest form because that's a bigger number. And then finally, you can do 8 times 25. So you get 5 square root of 8. And it's clear that can be made into a smaller thing. Just as this can be made into a smaller one as well. 25 times 2, and I can bring it out. But it's quite clear the smallest radical form that I get is 10 square root of 2. And because this is as small as I can get it, that's how I know. Well, this is a tricky one. And sometimes this is best seen in its fractionary form. And that means it's 3/2. But actually, you know what? The easiest way to do it is look at the internal thing. What is a cubed? It's a times a times a. And they're all square roots. Because this can also be expressed as this. Doesn't matter where you put the powers when they're all powers. Well, these first two cancel out. So you just get a times the square root of a. This is the simplest mixed radical form of that. And they're all pretty much like that. So the interesting thing about this one is the square root of y to the 6 is y to the 3. And that's your exponent knowledge, so that can come right out. But the x to the 5 is x times, well, look at it this way. It's x squared times x to the 1, like this. And it's clear that if I square root these first two, just x to the 2 comes out. X to the 2, like that. And the only thing that's left is x to the 1 in the square root. So it's interesting to note that even exponents will always have a square root. And odd exponents, you can break part of it down into that, and there's going to be that left over. To put it another way, in the square root, it'd be x to the 4 times x to the 1 is equal to x to the 5. And x to the 4 has a square root right there, leaving x to the 1 in the square root. Are they all going to be like this? Yeah. So now that we know a simple way of finding a square root with an odd function, this is simply going to be 5 times n to the 6 times to n to the power of 1. N to the power of 6 has a square root of n to the 3. So it's always going to have this. And this other one follows the same rule. It's minus 2n, in brackets, n to the 4 times n to the 1. And n to the 4's power is n to the 2. However, n times n to the 2 becomes n to the 3, but also with a square root of n. Now, even though, here's the problem. These technically, let's see if I got that right. N to the 3 came out n, 2n to the 3. Now, technically, these are all apples. It's just that you see, the trick here is they put n out here. But if you put that n back in there, it's n to the 7 as well. So these are all apples, and they're trying to fool you. So I got 5 apples minus 2 apples. I've got 3 n to the 3 square root of n, like that. If you want a simpler explanation, put this n back in to n to the 7. You get 5 minus 2, which is the 3. And then you simplify the n to the 7 into n to the 3 times square root of n. Kind of got to go back and forth on that one. And this last one, I mean, it's a difference of, is it a difference of 2 squares? No, but it's close. This is just going to be square root of pq. There's nothing you can do about that. This one's going to be minus p. This one's going to be plus 2q. And then this one is going to be minus 2pq. So the only apples here are plus 1pq minus 2pq. See, what you end up with is 2q. I don't know if it's going to let me do that there. 2q minus p minus square root of pq. Kind of ridiculous. So this one, the secret is by realizing very carefully how many square roots there are and just focusing on the internal one first. It would help to know if there's a square root of 496. And there is. There's 64. So that means this internal one simply becomes 64. Then we can just focus on this earlier one. What's the square root of 64? It's 8. So really they're asking us to simplify the square root of 8, which we know is 2 times the square root of 2, because it's 4 times 2 in here, and the 4 comes out. So the answer to that long, big one is simply 2 times square root of 2. And nope, nope. Okay, so the interesting thing about this one is that it would actually help us to put 2 as a fraction. Square root of 2 is the same as 2 to the half. So that means I can replace square root of 2 to the power of x like this. Now I can bring that fraction out and say, okay, well, this is the same as 2 to the power of x over 2, because in an exponent of an exponent, you just multiply them. Now all I have to do is find if there's a power of 2 for 256, and I happen to know there is. So I just got to figure out which one. To the power of 2 is 4, 3 is 16, 8, 4 is 16, 5 is 32, 6 is 64, and 7 is 128. So 8 is 256. So that means I can express 256 as 2 to the power of 8. Well, if 2 to the power of some unknown amount is equal to 2 to the power of 8, the rule is that x over 2, the exponent, must be equal to the other exponent. To solve for this, I multiply both sides by 2, and I get x is equal to 16. If you want to make sure that's true, we would now go back and find out if square root of 2 to the power of 16 is equal to 256. Now that's even easier solved if you again go back and say, well, this is half and the x is 16. What's a half times 16? It's 2 to the 8. And clearly 2 to the 8 is equal to 2 to the 8. Not as big of a mystery as they like to make it. And then that was that. That's all of it.